Let's look at another example. So we have a second order system. We have g equals to 1/2 s plus 1, and h is 1 divided by quarter s squared plus s. And we have negative feedback. Okay, and we want to determine the locus on the real axis. So if we compute the closed loop system's transfer function, which is k times g divided by 1 plus k times g times h, we are going to get this in the denominator. So only the denominator part, the characteristic equation, is going to be this. Now, this is not in standard form. We have to write it in standard form. How am I going to do that? I multiply the numerator and the denominator by 4. I'm going to have s squared plus 4s in the denominator. I'm going to have 2s plus 2 in the numerator. If I solve this, the poles are going to be 0 and negative 4, and the 0 is going to be at negative 2. So we have 2 poles and 1 0. Remember that in this case, if you have number of poles being more than zeros, we get a certain condition in the table. If you go back to the table, that tells us about the number of separate loci. If you have more poles than zeros, the number of poles is going to be the number of separate loci, which is 2. So I'm going to have 2 line segments in my root locus. The segments on the real axis that are in the locus now are going to be negative infinity to negative 4 and negative 2 to 0. Why? Well, look at the location of these three. So I have 0, negative 2, and negative 4. Remember, the real parts of the locus, so the segments on the real axis are in the locus if there's odd number of things on its right hand side. So if I look at points on the right hand side of the origin, so from 0 to infinity, there's nothing on its right hand side. That's not an odd number. If I look at negative 2 to 0, there is even number of, so if I look at the points between 0 or the origin and negative 2, there are even number of poles and zeros on the right hand side, right? There is this one pole. If I look at these points, there are sorry, I meant odd. So if I'm on this, so between the origin and negative 2, there is 1, which is odd number of poles and zeros on its right hand side. If I look at this segment between negative 4 and negative 2, there are 2 things on the right hand side. So 2 is an even number, so that this is not in the locus. And then if I look at negative 4 to negative infinity, I'm going to have 1, 2, 3 things on my right hand side. So 3 is an odd number, so all these points are in the locus. Okay, so we have learned how to prepare the root locus. We have learned how to find the segments on the real axis that are in the locus. Now we want to find the location and angle of asymptotes. Remember from previous courses what an asymptote means. The definition of asymptote is a line that continually approaches a given curve but does not meet it at any finite distance. So what that means is that we are going to have lines, or we are going to have vectors that a root locus is going to get very close to it, but it's never going to actually touch it. We don't always get asymptotes before trying to calculate the location and angle of them. We should make sure that we actually need them, otherwise we are just wasting time in the exam or whenever we are computing these things. If you do calculate them, it's not going to give you something wrong. It is going to actually tell you that, well, the asymptote doesn't exist, but you should be careful to not just compute it without really needing it. Let's show when we need asymptotes with an example. Look at this system. I have g and h given to me, and I want to plot the root locus of the system. So first multiply g by h. So what are the zeros and poles of the open loop system? Well, I'm going to have origin, -4, -4, -2, and -1, right? So 0, -2, -4, -4, and -1. This -1 is the 0, and the rest of them are poles. So if I locate them on the map, so I'm going to have the origin, -1, -2, -4, and -4. If I try to find the segments that are in the locus, I'm going to get this, the red lines. So here I have 1 pole on my right hand side, here I have 2, therefore it's not in the locus. Here I have 3, here I have 5, right? So here I have 1, 2, 3, 4, 5, therefore all the points from -4 to -infinity are in the root locus too. Okay, so now let's think about the story that happens. What we saw before is that, so let me go back to the table and show you. So what we learned before was that we prepare the locus to sketch, we factorize the transfer function, we locate the open loop poles and zeros, we determine the number of separate loci based on the number of poles and zeros, and then we locate the segment of the real axis that are root loci. We already did all of these. Now let's look at number 3. The loci proceeds to the zeros at infinity along asymptotes centered at sigma and with the angle phi, and we have the equation to compute them. Okay, but why do we need them here in this example? Because we should think about the story that poles and zeros are telling us. As we studied before, the loci always comes out from poles and goes into zeros. So when I know that I have this red line here, I can put an arrow that shows what happens to this pole and to this zero. So this pole, as I increase the gain, gradually moves and goes to here. That's the entire story of this pole, from gain equals to 0 to gain equals to infinity. This pole goes to the left and goes to negative infinity. So I know what happens to this pole. How about these two poles? These two poles, as we know, the arrows should come out of them. So these two poles seem to move out, okay, and then supposedly meet somewhere in the middle. So what do you think happens after that? Do you think when this pole and so the -2 and -4 meet each other somewhere in the middle, do you think they're going to pass each other? Do you think they're going to just stay there? Or do you think they're going to come out from the real axis? The correct answer is number 3. They are going to meet each other at some point and they both are going to leave the real axis. Okay, so they leave the real axis. What happens then? Well, they go to either infinity like this, or like this, or like this. So somehow they always go to infinity. So asymptotes teach me or show me the direction that these two poles are going to move. So in this case, when I realize that these two poles are going to meet somewhere in the middle, I'm going to say, oh, okay, now I need an asymptote. I need to find the location and I need to find the angle of asymptotes from the equations we saw before. So this is the equation that helps me to compute the location of asymptotes on the real axis, and this is the equation that helps me find the angle. So if n is greater than m, so number of poles is greater than number of zeros, as we studied, the number of separate loci is equal to the number of poles. But if I have more zeros than poles, then the number of separate loci is the number of zeros. Notice that root locus is symmetrical. Until now, we haven't really discussed this because we were only focusing on the real axis. Now that we are going to leave the real axis, symmetricity is something that you always should have in your sketches. And notice that the direction of the movement of poles is in root locus is from poles to zeros. Okay, now let's see examples. For the equations for this example we studied just now, let's compute the location and the angle of asymptotes. So this is the location, this is the angle. So for location, I need to add the poles and then subtract from them the zeros and then divide by the number of poles minus number of zeros. So my poles are -2, -4, and -4. So I'm going to add these up. -2, -4, -4. I'm going to have -10. Then you subtract from it -1. So -10 minus -1 is going to be -9. And then divide it by how many poles do I have? 3. How many zeros do I have? Sorry, I forgot this, but it doesn't really do anything in the numerator. So how many poles do I have? 1, 2, 3, 4. Divide by 1 is 3. Okay? So -2, -4, -4, and then subtract from it -1 and divide by 4 minus 1, you get -3. So the location of asymptotes is going to be at -3. How about the angle? So for the angle, I'm going to have 180 divided by the number of poles minus number of zeros, 4 minus 1, which is 3. So 180 divided by 3, which is 60, times 2k plus 1. So I'm going to have 60 times 2k plus 1. So 60, 180, 300. You can even go further, but so notice that like you can go for k equals to 3, but you're going to get 60 again plus 360. So you're going to get the actually these three angles again and again. So this is going to be the root locus at -3, right? -3, yeah, -3. I'm going to get lines with angles of 60, 180. So this is 60, this is 180, and this is 300. So what's going to happen to these two poles is that they meet each other, and then they are going to leave and follow these two lines. And I know which pole is going to follow this line to -infinity. It's this pole. So I found out the location and the angle of poles. One thing to notice before we go to the next slide is that so what we found was the location of asymptotes. We didn't find the location of where these two poles meet. So look at this figure. This is actually the root locus of the system. I think you can tell that the point that these two poles are meeting each other is not in between them. So in between them would be -3, and that's what we found for the location of asymptotes. So asymptote is different than the location that the poles actually meet. So asymptote is an imaginary line imagine a dashed line that I can draw here, and another one that I can draw here, and they're going to meet each other here at -3. But that's not what meeting each other for these two poles is. We are going to later compute that.